All right, so yesterday we were talking about scalar and vector quantities, okay? That obviously scalar quantities have only a measured value, okay, or a magnitude, and vector quantities have both magnitude and direction, okay? We looked at these fairly simple kind of displacement type questions, okay? Keeping in mind that, we had to assign positive and negative values if they were going in different directions. These were all one-dimensional vector analysis like you would have done in Science 10. Okay, so we're going to continue on with that kind of stuff, okay, where we're going to look at like the importance of a reference point. For example, back with the Inukshuk question previously, okay, we started here. This was our initial position, okay, and this was our final position over here, okay, but the only way we knew where our initial position was because we were given a reference point. Okay? We were told that the person started 1.5 meters to the right of the Inukshuk. The Inukshuk was a reference point. Lots of questions are going to give you reference points so that you know where the question begins and kind of where your initial position and final position are in relation to each other and that reference point. Okay? So we'll look a little bit at that today as well. So what I would like you guys to try right now is to try and do number 4. Okay, I want you to see if you can draw the seating plan that's listed there. That's all you have to do is just draw it out. Doesn't even really have to be to scale, okay, given the information in that question. In that question, who is the reference point?
I think it's Chad.
Okay.
It's Dolores.
It's Dolores. Chad is usually like the answer that I get because he's the first person lots of times that people draw because he's attached to a number. Dolores isn't. But I don't know where to put Chad unless I place Dolores somewhere. Okay? So Dolores actually acts as my reference point. Now, this is the trick. Do they tell me where she is? No. I just have to put her somewhere. Okay? She's going to be the reference point because I'm going to draw Chad 2 meters to her left. Okay? So Dolores is my reference point. And then I go from there. How many people have got the diagram done? Okay, I'll give you about another 10-15 seconds here to finish it up, and then we'll draw it here together. Okay, so I've marked Dolores as right here. I'm going to put Chad 2 meters to her left. Okay, so I'm going to just say that this is 2 meters right here. Okay. Ed is 4.5 meters right of Chad. So how many meters right of Dolores is he?
2.5.
2.5 meters, right? Him over here. Okay. Greg is 7.5 meters left of Chad. And Hannah is 1 meter right of Ed. Okay, so I've drawn that roughly to scale. Okay, I mean, I obviously didn't measure anything, but the 7.5 line is quite a bit longer than the others. Okay, what's the displacement of a teacher who walks from Greg to Hannah? So this is my initial position. That's my final position. Okay? 13 meters. Okay, so we got 7.5, 9.5, 12, 13 meters. Right, exactly. We've got to have a direction on that. Displacement's a vector quantity. Okay, so our total displacement would be 13 meters right. And if you don't write right, you'll be wrong. Okay. Is that making sense? The importance of a reference point. Okay, so reference points are super important. The first time I did this question, like the book was brand new that I took this out of, we had just moved into this building, didn't have smartboards, just the whiteboards. I drew Dolores right here and I started measuring. Greg is still on the door frame because apparently board marker doesn't come off of paint. it also means that since 2006, this door frame has not been painted. That's a long time to not paint. Just saying. All right. Let's have you guys try number 6. Okay, so this diagram goes with number 6. Okay, so despite the fact that this is not a very PETA-friendly question, because it involves using a racket made out of baby seals, okay, which in this day and age would not be cool, all right? We want to look at this from the perspective of scalar versus vector point of view of the movement of the ball. Okay, so this is where the ball starts. That's the initial position of the ball. It's tossed to the person here, and then that person fires it all the way over here, and this ends up being our final position. Okay, so the total displacement of the ball is pretty straightforward. Okay, it's 5 meters to the right. What's the total distance traveled? 11, yeah. The gut reaction is 8, right? Because we see on that diagram a 3 and a 5, and we just right away put them together. Okay? But what we have to do in a question like this is draw what we would call a vector diagram, which is I show the movement of the ball as arrows, and I draw them tail to head. So I've drawn that first arrow that's 3.0 meters. Okay? And then from there, the ball is sent here. Okay? Now, from that, I can clearly tell it's more than 8 meters, because now I see that extra long arrow that indicates it didn't just go 3 plus 5. It did the 3 part twice, okay? Which gives us a total of 11, because this would be 8 meters. Okay? So that's kind of introducing what vector diagrams are going to look like. We always draw our vectors represented by an arrow, okay? And we draw them tail to head. So it's kind of like telling a story with pictures. Okay? First it did this, and then I put my pencil on the head of that first arrow, and I draw the next arrow, and then I draw the next arrow, and so on and so on. Okay? All right. Okay. Using v equals d over t, just so that everybody's totally clear on the expectations for algebra in physics. Okay? Those are not allowed. Okay? They're very, very bad. Right? And this is like one of maybe 2 formulas on the entire formula sheet that it would actually work for. Okay? We cannot use triangles to manipulate equations in physics 20. Okay? Because the next formula we're going to use, this one, I don't know how you draw a triangle for that one. Triangles only work for 3 variable formulas, maybe a 4, if everything is either multiplied or divided. As soon as you put a plus or a minus or a square root or anything else in there, this method of doing algebra where you cover up the one you're looking for doesn't work anymore. Sorry, I can't not be mocking when I talk about triangles and algebra. I can't help myself. So yeah, guys, that absolutely is out. Okay, we just cannot use those because almost every formula we use is not going to work with a triangle. Okay, like at the end of the semester, we're going to be using a formula that looks like this. Got a triangle for that? Like, don't even think like a trapezoid or something would work for that one. Okay, it's just not going to happen. So if you've been using triangles, pay close attention. Algebra is not terribly difficult. There's only 3 rules to follow in algebra. Okay, and those 3 rules go as follows. If I want to move something, I perform the opposite operation. So if I'm multiplying, I would divide to move it to the other side. Okay. Second rule, what I do to one side, I do to the other side. Okay. And the third rule, I would move what's not attached to what I'm looking for first. Okay, that's kind of the tricky rule. So if we're using v equals d over t, okay, if I want to solve for d, what do I do with t? Multiply. Because right now I'm dividing by it, right? So I just, whoops. Do this. Multiply both sides by it. Okay, now I'm solving for d. What if I want to solve for t?
Same thing, you're going to multiply and then you're going to divide both sides by v.
Right. Okay. And why do I not just move d?
Because you can't, because it's on the top.
Right. Okay. If t is on the bottom and I move d, I'm not solving for t, I'm solving for 1 over t, which is the opposite. Okay. 1 over t is not the same as t, because 1 over 2 is not the same as 2. Everyone follow? Okay. But I see people, they make that mistake, and it's an innocent mistake. But we got to make sure that we don't ever try and solve for something if it's on the bottom of an equation, because we're actually solving for its inverse, not the actual value. All right, and then yeah, like we said, like Tony said, we would just move this over by dividing, and now we're solving for t. Okay, you can always double check your algebra by looking at the units and seeing if you get the units for what you're looking for. Like when I do this, I know I'm going to get seconds because I'm going to be dividing meters by meters per second. The meters are going to cancel, and I'll be left with seconds, and I'll be good. Okay? All right, so if I wanted to use all 3 rules of algebra, okay, if I wanted to use all 3 rules of algebra, then I would do this. Let's say we're looking at this formula. This is one you guys would have used last year. Okay, if I want to solve for m, what should I move first?
Subtract the b.
Yeah, move b. b is not attached to m. Okay, so I would move it first. And I would do the opposite. I would subtract. So y minus b equals m times x. I want to get m by itself. What do I do with x? Divide over the other side. Okay, boom. Now I'm solving for m. Okay, guys, honestly, those 3 rules can get you through any non-calculus based science class. Okay, it got me through university physics because I didn't take any that wasn't nonlinear. Okay, because calculus frightened me and I didn't do very well. Like, I memorized the examples in the textbook and wrote them down on my final exam and got part marks for method, which was still smarter than half the people in my class. But okay, yeah, I found it very difficult. Math, believe it or not, as a physics teacher, is not my strong suit. Okay, but I can do algebra because it's like junior high math really, really well. Okay, those 3 things, those 3 rules will get you a long way. Just don't forget them. All right, this is one like you would have had back in Science 10. Okay, so I want you guys to write it down as our first kind of average velocity example, or kind of 2-step problem here. And then see if you can solve it. I'll give you a few minutes to get ahead of me, and then we'll walk through it together. Okay. You guys have been working on that one for quite a while. So if I want to calculate the average, I should just take 4 and 16 and add them together and divide by 2? Why will that not work here when it's a perfectly valid way to find averages?
Because of the amount of distance you travel, I guess.
Yeah, exactly. Adding all of your items together and dividing by the number of items is a perfectly valid way to calculate an average, provided all those things you add together represent equal parts of the total. In this case, we need to do a weighted average because these 2 parts of the trip do not represent equal parts of the trip. One of them is considerably longer than the other. Okay, we have one that goes for 12.5 seconds, and the other one, well, goes 26 meters and 16 meters per second. It's only going to take a couple of seconds, actually less than a couple of seconds, for that part to happen. So it is a much smaller part of the whole trip. Okay, so it's kind of like this. If I drive all the way to Edmonton, and I'm able to go 120 the whole way there until I get to like the very south end, and for the last kilometer, there's construction and I have to slow down to 50 for the last kilometer. Should I go 120 plus 50 and divide by 2 to get my average velocity? Hell no, okay? My average velocity is going to be like 119, okay? Because I went 120 for 99% of the trip, okay? That last little bit, okay, I slowed down. That doesn't make my average like hugely decreased. Does everyone kind of follow the logic there? Okay, so here's what we need to understand about the two formulas we learned yesterday, okay? This formula actually means average velocity equals total displacement divided by total time. We never write those things in there, okay? But it's inferred by that formula. The same is true for this one. Okay? Vector or scalar, okay? It's average equals total over total. Doing it that way will weight the average in favor of the bigger part of the trip. Okay? So if I want to find the average velocity, this is the formula I want to use at the end. Okay? I'm not quite there yet. So what I want to do first is write down all the things the question gave me. In part 1, it says that the garbage truck traveled 4 meters per second north. Okay? And it did that for 12.5 seconds. Okay? And then it travels 26 meters south at 16 meters per second. Okay, so that's what the question tells me. Now, if I want to calculate the average velocity, I need the total displacement and the total time. Well, I don't know the displacement for part 1, and I don't know the time for part 2. Can I find them? Yes. Okay, so I got to do a little bit of V equals d over t to start things off. All right, so I'm going to be looking for d in part 1, so I'm going to multiply t times v. All right, so that'll be 12.5 times 4. Okay, so that should be 50. Okay, 50 meters north. All right, so now I've got my displacement for part 1. All right, I want to find the time for part 2, so I manipulate. I got t equals d over v, so 26 divided by 16. Sorry, forgot to fire up my calculator. All right, so 1.625 seconds. All right, so are we seeing a pretty big difference here in terms of how much of this trip is part 2 and how much of this trip is part 1? Like, it's almost 90% part 1. Okay, in fact, it's probably a little bit more than 90% part 1. Okay, it's 12.5 seconds of the total. Okay? It's a big difference. All right, so now that I've got the time for both parts and the displacement for both parts, now I can work on those averages and totals. Okay? The total displacement, I went 50 meters north and 26 meters south. What's my total displacement, Tom?
24 meters north.
24 meters north. All right. What's my total distance traveled? 76, right, okay, because I went 26 and then I went 50, or actually 50, then 26, 76 meters, okay? That's scalar, so I don't put a direction on it. All right, and I need to get my total time, okay, so 12.5 plus 1.625 is going to be 14.125. I shouldn't do math in my head. Or maybe I should. I probably just got lucky today. Okay, 14.125. Okay, so now I've got everything I need to use these two formulas. Okay, I can calculate the average velocity by going 24 meters north divided by 14.125 seconds. All right, so our average velocity here is going to be 1.7 meters per second north. Okay. Everybody all right with that one? And then to get the average speed, okay, I plug in my distance instead of my displacement, so I'd have 76 divided by 14.125. All right, so we got 5.4 meters per second. And no direction on that because it's speed and speed is scalar. That ringing a bell from Science 10? And we definitely would have done questions like that, right, in Science 10. All right, so basically the whole purpose of that question is to remind you about how this formula, or what this formula really means, even though the average and total is never actually written anywhere else. Okay? All right, questions there? Okay. Okay, I would like you guys to try that one. It's very similar to the one we just did. All right, so similar to the one we just did, except this one's all scalar. Okay, there's no directions or vectors to be concerned with. Okay, bus travels 11 kilometers. Okay, so we know in part one, okay, the distance is 11 kilometers, and it does that with an average speed of 21 meters per second. Okay, what problem do I see right now?
Units.
Units. Okay, my distance is in kilometers, my speed is in meters per second. That's like dividing apples by oranges. Okay, I don't know what that equals, okay, but I can't divide kilometers by meters per second. So I need to convert either either the speed or the distance to another set of units. Okay, since speed has two sets of units, is it easier to convert the distance? Okay, how many meters in a kilometer? 1,000. All right, so how many meters is this?
11,000.
11,000. All right, so simple conversion there, but just know your units always have to match. Okay, and then in part two, okay, we go 1 kilometer, so 1,000 meters. And at 4.2 meters per second. Okay, find the average speed of the bus for the entire trip. Well, okay, what do I not have that I'm going to need to get that? Time. I don't have the time for either part, so I'm going to have to do a little quick calculation here of d over v to get my times. Okay, so we'll have 11,000 over 21. Okay, so that's 523.8. And by the way, guys, I'm rounding off on the board, but I'm keeping all my decimals in the calculator. It is crucial that you do the same. Okay, we have to maintain the accuracy of our numbers. We don't want to round off until we do our significant digits. Okay, at the end. How many people know what I mean when I say significant digits? Okay, good. We'll just quickly go over that in a couple of days, but I kind of figured most of you knew it already. Okay, and then for part two, 1,000 over 4.2. All right, 238.1 seconds. All right, now I can do the total distance and the total time. So average speed is going to be 12,000 meters, okay, divided by 61. I'm not doing that in my head. Okay, so 12,000 divided by. All right, 15.75. We only have two significant digits there, so we're looking at 16 meters per second. Okay. Make sense to everybody on that one?
Yep.
Okay. All right, I'm going to give you guys a little break here. Let's say we'll reconvene here at 9:24. Okay, just like a break within the classroom. If anyone needs to use the washroom, okay, I can only let one go at a time. Yes. Okay. Okay. So in this one, we got a trip consisting of 3 parts. Okay, so the first thing we want to do always is write down what we know. Okay. First part, we've got a velocity of 25 kilometers per hour north. Okay. For the first 15 kilometers. Okay, in part 2, we know that it is going to move at 62 kilometers per hour due north. And that's for 32 kilometers. And then in part 3, at what velocity does the car travel for the last 13 kilometers? So part 3, we at least know how far it is. Okay, if I'm going to find the velocity in this part of the trip, what do I not know? The time, yeah. I need the time for part 3. Well, problem. I don't have the time for any of them. But I do have the total distance of the entire trip and the average velocity of the entire trip. So I can go over here and make a 4th column that are my totals. Okay? I know the average velocity is 40 kilometers per hour. And that my total displacement is 60 kilometers north. Okay, what can I find with those two numbers?
Total time.
Total time. Can I find the time for the other 2 parts? Okay, would that allow me to, by process of elimination, figure out how much time is left for the last one? Okay, so there's a lot of like intermediate calculations, intermediate steps in this one. Okay, I would never give you one like this on a unit exam because it's like the same step 3 times. It's testing the same thing a whole bunch of times, but okay, you know, just as an exercise to practice things, it's good. So T equals D over V, so that's going to be 60 over 40, which will be 1.5 hours. Okay. So now I can find out what the time is for these ones. Okay, so time is going to equal D over V, so 15 over 25. All right, so that one takes 0.6 hours. Okay, this one here, 32 over 62. Weird. Okay, so 0.516 hours. All right, well now that I know those and I know what the 3 of them add up to, I can find the one I'm missing. All right, I'm just going to take the 1.5 and subtract 0.6 plus 0.516 with all the decimals. All right, so the last 13 kilometers takes 0.38 hours. I divide those two things, I should get the average velocity, because v equals d over t. Okay, so take my 13 and divide it by the time I calculated there, 34 kilometers per hour north. Okay, so yeah, there's a lot of intermediate steps on a question like that. It's a bit tedious, to be certain. All right, so let's have a look at unit conversions here, because we haven't talked about these yet, or what we call compound conversions. If I had to convert, like, let's say, a velocity or a speed from like kilometers per hour to meters per second, okay? It's not as simple as just dividing by 1,000, okay? Because we got two sets of units to calculate. All right, so let's just quickly look at how we would do that. Okay, so the most common compound conversion you're going to have to do in Physics 20 is converting kilometers per hour to meters per second. Okay, so if I have, let's say, 100 kilometers per hour, and I want to convert it into meters per second, I have to convert both the kilometers to meters and the hours to seconds. Which number do you suppose is going to be bigger? The number of kilometers I would go in an hour, or the number of meters I would go in a second?
Kilometers in an hour.
Yeah, kilometers in an hour is going to be the bigger number. Okay, the number of meters I would go in a second would definitely be a smaller number. Okay, sometimes we kind of have to ask ourselves questions like that so that when we get to the answer, we can go, yeah, that makes sense. Okay, or no, that doesn't make sense. All right, so I have to convert both kilometers and hours. So what I'm going to do first, not equals, is I am going to convert the kilometers to meters. All right, so what I do is I multiply by the conversion factor. In 1 kilometer, there are how many meters? 1,000, right? So I would multiply the kilometers by 1,000. That'll turn it into meters. Okay, so by doing this conversion, I end up with kilometers on the top, kilometers on the bottom, and the kilometers are gone. Now they're in meters. Okay, now I have 100,000 meters per hour. Okay, but I don't want meters per hour, I want meters per second. So I'm going to put 1 hour on the top. How many seconds in an hour?
60.
That's such a knee-jerk reaction. Everybody wants 60?
3,600.
3,600. 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600 seconds. All right, now I got hours on the top, hours on the bottom, and they're gone. So what this comes out to is I'm going to have to take my 100 kilometers per hour and multiply by 1,000 over 3,600. And can I simplify that? Could I say same thing? Okay. And could I then just go 100 divided by 3.6? I totally could, because 100 times 1 is 100, and then divide by 3.6. Okay, so this is how you do a compound conversion, but for kilometers per hour to meters per second, or vice versa, the magic number is 3.6. Okay, so if I want to go from kilometers per hour to meters per second, I would divide by 3.6. If I want to go from meters per second to kilometers per hour, I would multiply by 3.6. Okay, that's kind of the magic number. But, and you'll eventually just know that one because you'll do it so often. But any compound conversion is done as we did that one. We convert one unit, and then we convert the other unit, and we just multiply it through. Okay? It's just for this one, because we do it so often, it's nice to have the shortcut. Okay? Everyone all right with that? Okay, just gonna say, like, it comes up once in a while. All right. Now, what we're gonna move to tomorrow is we're gonna start into position versus time graphs, okay, which is gonna be familiar because we did those in Science 10, okay? But just kind of a couple of bits of review here for position versus time graphs. Okay, so we got position in meters, time on the x-axis in seconds. Okay? When I look at a position versus time graph, should I be able to tell what the object is doing? So if I had a position versus time graph that had a horizontal line on it, what is that object doing?
Moving.
Staying in one place. Okay, why? Because its position is not what? It's not changing. Its position is staying at whatever this value is, 5 meters. Okay, it's at a position of 5 meters, and that isn't changing. Anytime you have a horizontal line, whatever's on the y-axis isn't changing. Okay, if this was a velocity versus time graph, then the object would be moving, but it would be moving at a constant velocity. Okay? In this case, it's at a constant position, which means it isn't going anywhere. Okay? What is this doing?
Slowing down.
If it was a velocity versus time graph, yes, it would be slowing down then. But this is showing position.
It's moving backwards.
Moving backwards at,
A high rate.
yeah, constant rate. High, it could be a high rate. We don't know for sure, but it could be a high rate. Okay? But it is a constant rate for sure, right? Because its position is changing by the same amount every time interval. Right? It's moving backwards at a constant velocity. Okay? What's it doing now? It's accelerating. Okay? Now it's moving forwards, but because it's not a diagonal line, it's curved. That means each second it goes farther than it did the second before. And the only way you go farther than the second before is if you're going faster. Okay? So that object would be speeding up. What would this object be doing?
Decelerating.
That object is slowing down. Okay? Go back to this. Here, this object was doing what? It wasn't moving. Well, this line gets flatter and flatter and flatter, does it not? Eventually it is flat at the top, so that means it's slowing down because eventually it comes to a stop. Okay? Being able to read and interpret a graph is going to be one of those super important skills for this course and Physics 30. Okay? We only go over a handful of graphs in Physics 20, but in Physics 30, you'll go over like 30 or 40 different graphs. So being able to interpret a graph and just go, okay, here's what's on this graph, so this is what it means. Okay? Being able to do that is really important. Okay? All right. So for tomorrow, okay, you will have a quiz tomorrow. I'm going to post it on Google Classroom at 3:30 today. It'll be on B equals D over T. Okay? So the stuff we worked on today. And then we'll get into reading position versus time graphs. And then on Monday, we're going to do our lab on position versus time graphs. Okay, so that's kind of where we're headed over the next couple of days. This is your day, or you guys are taking off tonight?
Yeah.
Okay. All right. Yeah, so just watch the podcast. Okay, any questions on the stuff we covered today? All right, just, I know there's still, a bit of time left, but I just can't really get into what I want to do tomorrow without really getting nothing out of it. Okay, so we'll flip there.